A cliff railway in Devon, England, has been carrying passengers up and down a cliff face since 1890, and it has never once had an engine installed in either of its two cars. No motor, no electricity running the cars, just two train cars, a steel cable and plain water. That's genuinely the entire power source, and it still works exactly the way it did more than 130 years ago. But the free part isn't quite as free as it sounds. So, how does a train actually move without anything generating power? Start with the basic shape of the machine, because it isn't really a train in the usual sense at all. It's a funicular, two cars connected by one long cable that runs up the slope and around a single pulley at the top. When one car goes up, the other comes down. Always. Because they're physically tied to opposite ends of the same cable, like a seesaw laid out along a hillside instead of balanced on a fulcrum, pivoting on a wheel at the summit instead of a point in the middle. That alone doesn't explain the motion though, no matter how sturdy the cable or how well-oiled the pulley happens to be. Two equally weighted cars connected by a cable just sit there, balanced, going nowhere, no matter how long you wait. Perfectly still, perfectly useless, something has to tip the scale. That something is water, and the trick is almost embarrassingly simple once you see it. Each car carries a tank underneath the floor, built into the frame, so the extra weight sits low and doesn't destabilize the car on the slope. At the top of the slope, that tank fills with water pumped or piped in from a reservoir, adding several tons of extra weight to a car that's already sitting at the highest point of the track, a slow, steady process that takes a couple of minutes for the whole tank to fill. Once it's heavy enough, gravity takes over completely. The loaded car starts sliding down the slope, and because it's tied to the other car through that cable and pulley, its descent physically drags the lighter car up the hill at the exact same time, at the exact same speed, the whole way, neither car ever able to outrun the other, since the cable length between them never changes. At the bottom, valves open and the water drains away, back into a tank or a stream, and the car that just arrived is now light enough to be pulled back up on the next cycle by whichever car gets filled next. Here's the part that actually explains why this works so well instead of just barely working, and it comes down to something almost nobody thinks to ask about a seesaw. The two cars are already close to the same weight before any water gets added, so the system isn't fighting itself to lift dead weight up a mountain the way a plain hoist would, straining a motor against the full weight of everyone and everything inside the car. It only has to overcome friction, the drag between wheels and rail, the resistance in the pulley, the small energy losses that show up anywhere metal moves against metal. That's a tiny fraction of the total weight involved, nowhere close to what it would take to haul an entire car up a slope from a dead stop, the way a plain elevator motor has to lift its whole cabin against gravity with nothing helping from the other side. A few tons of water is more than enough to supply that fraction and still have force left over to pull the ascending car the entire way up. The engine, if you can even call it that, only ever has to solve a small problem, because the big problem, actually lifting a train car's worth of mass, gets cancelled out automatically by the car coming down on the other end of the same cable. Nobody has to calculate that cancellation in real time, run any numbers, or adjust anything mid-trip. It just happens every single trip as a direct consequence of how the two cars are connected. The same way it happened on the very first trip back in 1890. This idea is a lot older than the average person assumes when they first see one of these things running, gliding up a hillside without a sound, and guesses it must be some clever piece of 20th century engineering. The earliest known version wasn't Victorian at all, and it wasn't built to move passengers for fun either. A cable-hauled incline at Hohensalzburg Fortress in Salzburg, Austria, dates back to around 1495, built to haul supplies and building material up to a fortress perched on a hill overlooking the city below, originally powered by prisoners or oxen hauling on wooden tracks instead of water, centuries before anyone had built a steam engine, let alone an electric motor. Christopher Columbus had barely finished his first voyage by the time that fortress incline was already carrying loads up its slope. The counterweight idea came first, older than the modern nation of Austria itself, dating from an era when most of Europe still moved goods by ox cart and river barge. Water was just a smarter way to generate the pulling force once someone figured out gravity could do the same job an ox was doing, for free, as long as there was a water source at the top of the hill. Not every water-powered line stayed elegant though, and one particular example takes the idea somewhere genuinely strange. A funicular in Freiburg, Switzerland, runs on wastewater. Actual sewage, collected from the town above, flows into a 100,000-litre reservoir before being routed into the railcar's tank, treated as just another gravity-fed fluid rather than something to be pumped away and forgotten, repurposed instead of simply discarded. It only takes about 1,500 litres to pull the other car up from 60 metres below, and the whole tank fills in around 3 minutes. Fast, efficient, slightly disgusting to think about too hard, once you know exactly what's filling that tank. The system was designed that way on purpose, partly as a clever way to manage the flow of water through the town's drainage below. A city literally engineered its sewer output to double as a transit system, and it's been running that way for well over a century. Not every water ballast railway survived to see the modern era, and the reasons why are just as practical as the reasons the idea worked in the first place. Filling a car with several tons of water every single trip means the whole system carries enormous weight, and that weight puts real, constant strain on the axles, the wheels, and the track itself, wear that adds up trip after trip, year after year, in a way lighter passenger-only cars never have to deal with. Maintenance costs climb fast when every car in service is effectively a rolling water tank, and a rolling water tank is a heavier, harder thing to keep in good repair than an ordinary passenger car ever needs to be, especially once corrosion and mineral buildup start working on decades-old plumbing hidden away under the floorboards where nobody thinks to check it. Several early water ballast lines in Germany and Switzerland eventually got converted to electric motors instead, trading away the elegance of free gravity power for the simpler math of a motor that doesn't care how many tons of water are sloshing around underneath a passenger car and doesn't need a nearby reservoir large enough to keep refilling tanks all day long. Britain has more than one surviving example of this, and the details vary in ways that show how far people took the same basic trick. The Saltburn Cliff Lift in North Yorkshire opened in 1884, 6 years before the Devon line, and still uses a water tank holding around 1,100 litres in each car to make the same short, steep run it always has, a track barely 60 metres long but angled steep enough at around 35 degrees to make the physics obvious to anyone watching from the beach below. Small tank, short track, same principle scaled down to fit a modest seaside cliff instead of a mountain. There's a small design detail in many funiculars that people rarely notice until it's pointed out. Even though the track itself runs at a steep angle, the floor of each car is built level, stepped like a staircase relative to the car's frame, so passengers stand and sit on flat ground the entire ride, instead of tilting with the slope the way they would in an ordinary rail car, forced onto the same grade, luggage, and all staying exactly where it was set down. Riding a funicular doesn't feel like riding up a ramp. It feels like standing in a normal room that happens to be quietly climbing a hillside around you, an illusion of stillness built entirely out of careful carpentry. Not every funicular even needs a separate second track for each car. Some run on just 2 rails, with both cars sharing the same pair and passing each other at a widened section halfway up. A moment that can startle first-time riders who weren't expecting to meet the other car head-on mid-slope, close enough to wave through the glass. Others use 3 or 4 rails to keep the cars fully separated the entire way, trading a bit of extra track and construction cost for a bit less drama in the middle of the ride, and a bit more room for error if a cable ever needed emergency maintenance mid-route. The Monongahela Incline in Pittsburgh, opened in 1870, still runs today as one of the oldest continuously operating funiculars in the United States, carrying commuters up a hillside. The city was never going to flatten out just to make room for an ordinary road, over 150 years and counting of daily use. None of that variation changes the underlying physics. 2 cars, 1 cable, gravity doing the arithmetic every single trip, whether the track has 2 rails or 4. A handful of lines never made that switch though, and they're still running on nothing but water today, doing the same job in the same way as they always have. The Nürburgbahn in Wiesbaden, Germany, still fills its tanks the same way it did when it opened, climbing a 26% grade in about 3.5 minutes without burning a single unit of fuel, powered by nothing more complicated than gravity and a valve, carrying passengers up the same hillside it always has. The Cliff Railway in Devon, the one that opened this whole story, still runs the exact same way it did in 1890, still filling and draining the same 2 tanks under the same 2 cars, connected by the same basic idea a Victorian engineer worked out well over a century ago. No engine has ever been installed in either car in over 130 years of continuous operation, through 2 world wars and every technological revolution that followed them, through decades where nearly every other form of transport around it switched to diesel, then electric, then something newer still. So the actual reason this railway runs without an engine isn't that engineers found a way to eliminate power from the equation entirely. It's that they found a system clever enough to need almost none of it. A trick so simple it barely looks like engineering at all until you try to explain why it works. 2 cars, 1 cable, and just enough weight to nudge gravity into doing the rest of the job for free. The no engine claim is technically true and slightly misleading at the same time, a phrase that sounds like it's describing an absence when it's actually describing a very clever substitution, because gravity and water were doing the work of an engine the whole time. They just never needed fuel, a motor, or a single moving part beyond a cable and a pulley to do it. And they've been doing it since long before anyone thought to call it engineering, back when it was just a clever answer to a heavy problem. So here's the question worth sitting with. If a 500-year-old idea can still out-elegant most of what we build today, still running on nothing but a cable, a pulley, and whatever the local water supply provides, quietly outlasting steam, outlasting 2 world wars, outlasting entire generations of newer technology built to replace it, how many other obvious modern solutions are we reaching for simply because we forgot to ask what gravity could have done for free?